These are notes on the mole. In your book, it's 10.1 and 10.2. And I really recommend, especially if you're struggling, that after you take your notes, you follow up with the book. It gives you great questions and sample exercises that you can do to really help understand the material. So this is what's known as a mole map, and this is actually in your book. It's towards the end of 10.2. And basically, you have the mole here in the middle. And we talked about moles earlier this year, and we talked about them in terms of the number of representative units. So we said that 1 mole is 6.02 times 10 to the 23rd somethings. So if you have a mole of bananas, it's 6.02 times 10 to the 23rd bananas. If you have a mole of sodium atoms, it's 6.02 times 10 to the 23rd sodium atoms. But the mole is also related to mass. So down here we have, you can go back and forth between mass and the mole. And it's also related to the volume of a gas at this thing called STP, and we'll talk about that later. And so you can use a mole map to get from any one of these to another. If you want to go from the number of units to mass, you can change the number of units to moles, and then moles to mass. If you want to go to mass to volume, you can say go mass to moles and moles to volume. So the first thing we're going to look at is the relationship between number of representative units and the mole. And I want to start here because this is going to be review, since we already talked about this when we were doing converting between units. So if we want to look at moles to number of particles, or earlier I said number of representative units, just number of things. Sometimes you'll even see like moles to numbers. So what we need to remember is 1 mole is 6.02 times 10 to the 23rd units. So here's a sample question. How many atoms of carbon are there in 2.50 moles of carbon? So I highly recommend pausing the video, figuring this out, and then looking at the answer. Okay, so you should have gotten 2.50 moles of carbon over 1, that's what you were given, times 6.02 times 10 to the 23rd atoms over 1 mole of carbon. That's your conversion factor. Remember, it's got to be an equivalent amount. So 6.02 times 10 to the 23rd atoms equals 1 mole. And so your answer is 1.51 times 10 to the 24th atoms. And as you can see, the moles cancel. So now going in the other direction, how many moles of carbon are there in 1.00 billion atoms of carbon? You can set this up and you start with 1.00 times 10 to the 9th, which is a billion, atoms of carbon. And then, of course, we have our conversion factor, 1 mole of carbon over 6.02 times 10 to the 23rd atoms of carbon. This time we put the atoms on the bottom because, again, we want those to cross-cancel, so we can cancel this atoms with that atoms. And that gives us 1.66 times 10 to the negative 15th moles of carbon. So in that way, you can go between moles and number of particles in either direction, as long as you have your conversion factor. 1 mole is 6.02 times 10 to the 23rd. So, going back to our mole map, we've looked at moles and number of representative units. Now let's look at moles and mass. So I'm choosing this one second because I think it's the kind of middle concept as far as volume of a gas at STP. We're introducing a new concept, and that's STP. Whereas mass, we already know what mass is, so the new concept is converting between moles and mass. So when we're converting between moles and mass, I suppose it should say between moles and mass, not moles to mass, because we can always convert mass to moles. One of the things to note is that the molar mass of an element is its average atomic mass. Little typo there. 1 mole of sodium, for example, has a mass of 22.990 grams. At this point, I recommend getting out your periodic table if you don't already have it out. And just know that depending on what periodic table you're looking at and how many significant figures it uses, your numbers may be slightly off from my numbers. Obviously, mine is to a pretty good limit of precision because it's 3 decimal places. So, what is the mass of 2.50 moles of sodium? So go ahead, again, figure that out, pause the video, and then check your answer. So you should have gotten 2.50 moles of sodium. And then our conversion factor in this case comes from up here and also from your periodic table, but I did give you this one where we said 1 mole of sodium equals 22.990 grams. So in order to cross cancel, we want our moles of sodium down here. 1 mole is 22.990 grams of sodium, giving us an answer of 57.5 grams of sodium. And so we could say 2.5 moles of sodium equals 57.5 grams of sodium. So that's really helpful. A lot of times when you're mixing chemicals in a lab or you're preparing chemicals for an experiment, you'll know how many moles you need, and knowing that is great, but we don't have anything that actually measures moles. We have balances which measure grams. So in order to know, oh, I need 2.50 moles, now I can use a balance and say that's going to be 57.5 grams. So converting the other way, how many moles are in 55.6 grams of NaCl, sodium chloride? This is a little more complex because sodium chloride obviously isn't on the periodic table. Sodium is and chlorine is, but there's no sodium chloride. And so this is where you need to find the molar mass of sodium chloride. You actually had to find the molar mass in your the most previous lab you did, the evaporative cooling lab, where you're supposed to find the molar mass of all of those compounds. In talking to some of you, I figured out that some of you actually figured out how to do this. Others of you, it turns out, simply Googled the molar mass and looked it up and then wrote it down. So now you actually need to learn how you find the molar mass. It's quite simple. So NaCl has 1 sodium and 1 chlorine. So we look up the molar mass of sodium, which is 22.990 grams, plus the molar mass of chlorine, which is 35.453 grams, and that's a total of 58.443 grams. So the molar mass of sodium chloride is 58.443 grams. One thing to note is, in this case, we had 1 sodium and 1 chlorine. If we had some other compound where there were 2, say we had sodium oxide, which would be Na2O, you'd have to add the sodium twice or multiply the sodium's molar mass by 2. So just keep that in mind. The subscripts absolutely matter because you have more of that substance. So then we can plug this in to our equation. We can say the question was how many moles are in 55.6 grams of NaCl. So we start with our 55.6 grams of NaCl. And now we know that 1 mole of NaCl is 58.443 grams. And so again, we put our grams on the bottom so that we can cross cancel. And then that gives us 0.951 moles of NaCl. And so that's how we can convert between moles and mass. And so then our last equality is between moles and volume of a gas at STP. And we're going to talk about what STP is in just a second. So moles to volume of a gas. At STP, which stands for standard temperature and pressure, standard temperature being 0 degrees Celsius and standard pressure being 1 atmosphere, which is sometimes abbreviated to 1 atm, 1 mole of gas occupies 22.4 liters. We're going to talk a lot more about STP when we talk about gas laws later this year, but I just wanted to give you a frame of reference for what STP is. So gases can change their volume based on the temperature and based on the pressure. Obviously, liquids and solids do as well. So liquid water, when it's close to its boiling point, actually takes up more volume than when it's at room temperature. But it's such a small amount that oftentimes we don't even consider that. But gases actually change quite a bit based on the temperature and the pressure. And so that's why we need to define what standard temperature and pressure is going to be so that we all have common vocabulary. So, what is the volume of 2.00 moles of oxygen gas, O2, at STP? So we know that at STP, 1 mole of gas is 22.4 liters. So we could set that up as 2.00 moles of O2. And then we want our 1 mole of O2 on the bottom, so the moles cross cancel. 1 mole of O2 is 22.4 liters of O2, which is 44.8 liters of O2. So that's a pretty simple calculation. So let's kind of bring all of this together here and go from mass, or from liters, all the way to mass. So what is the mass of oxygen gas in 5.74 times 10 to the 6th liters, which is roughly the size of a Goodyear blimp? So Goodyear blimps are filled with helium, not oxygen. Oxygen being incredibly flammable, make the Goodyear blimp very unsafe, but this will give you kind of the size of what we're looking at. By the way, for all of you who say, when am I ever going to need to convert in my entire life? About 20 minutes ago when I made this PowerPoint and was trying to find the volume of the Goodyear blimp, the Goodyear blimp website actually gives the volume in cubic feet. So I had to convert all the way from cubic feet down to cubic centimeters to milliliters and then up to liters. So it is useful. Alright, so what we need to do, actually pause the video as always and then go ahead and restart it when you think you have an answer. So here we're going from mass all the way to liters. So thinking about the mole map, you want to go mass, back to moles, and then over to liters. So we have 5.74 times 10 to the 6th liters, which was our given. And then we're going to convert liters to moles. So we're going to cross cancel the liters, so we put our 22.4 on the bottom. Actually, now that I'm saying this, I think I said it opposite. We want to go from liters to moles to mass, not mass to moles to liters. So we're going to cancel our liters, and that's going to leave us with moles. And then we can set up the second part. Now that we have the moles, we want to cross-cancel the moles and go to grams. So 1 mole of oxygen gas is 31.998 grams of oxygen gas, which is, looking at the periodic table, at oxygen's molar mass times 2, because oxygen gas, remember, is O2. And so if you solve all of that, you get 8.20 times 10 to the 6th grams of oxygen gas, which seems like a lot of oxygen gas, or quite a large mass of oxygen gas. We often think of gases as, quote, almost weightless, whereas this seems like a substantial mass of oxygen. So let's convert that, though, to pounds, which sadly we here in America are more used to. What would the mass be in pounds, knowing that 2.2 pounds is 1 kilogram? So go ahead and convert that just to give us a frame of reference. What is 8.20 times 10 to the 6th grams? So you would set it up like so, 8.20 times 10 to the 6th grams. And then we want our grams to cancel. So we say 1,000 grams is 1 kilogram. Then we want our kilograms to cancel. We say 1 kilogram is 2.20 pounds. And when we solve for that, we find it's 1.80 times 10 to the 5th, or approximately 18,000 pounds of oxygen gas, which again seems like a pretty massive amount. You could go through and figure this out for helium, as a matter of fact. Why don't we make that our warm-up question tomorrow to see, okay, but it's not oxygen gas that's in the Goodyear blimp, it's helium. What is the mass of that helium in the Goodyear blimp? And let's do that both in grams and in pounds. Again, just for a good frame of reference. Please feel free to put any questions you have on the comment section of YouTube, or please ask them in class tomorrow. Have a good night.